According to the first postulate, an electron in an atom could revolve in certain stable orbits without losing energy continuously. This means each atom exists in a definite stable state, and each existing state has a definite total energy. These are called the stationary states of the atom.
The electron revolves around the nucleus only in those orbits for which the angular momentum L is an integral multiple of a constant equal to mh by 2 pi, where h is Planck's constant equal to 6.625 into 10 to the power minus 34 joules second. Therefore, the angular momentum L of the electron is equal to mvr, which is equal to nh by 2 pi, where m is the mass of the electron, v is its velocity, r is the radius of its revolving orbit, and n is an integer. Let this be equation 1. According to Bohr's third postulate, an electron might make a transition from one specific non-radiating orbit to another of lower energy. When it does so, a photon is emitted having energy equal to that of the energy difference between the initial and final states. Then, the frequency nu of the emitted photon is given by the relation h nu is equal to EI minus EF. Here, EI is the initial state energy and EF is the final state energy of the electron. Let this be equation 2. Let us now derive the expression for the radius and energy of the hydrogen atom. From equation 1, we can write mvnRn is equal to nh by 2 pi. Here, n is an integer, Rn is the radius of nth possible orbit, and Vn is the velocity of the electron in the nth orbit. Let this be equation 3. The allowed orbits are numbered 1, 2, 3, and so on, according to the values of n, which is called the principal quantum number of the orbit. We have learned that the relation between the radius r of the electron orbit and its corresponding velocity v is given by Rn is equal to E square by 4 pi epsilon naught mvn square. Let this be equation 4. Substituting the value of Rn in equation 3 and simplifying, we have Vn is equal to E square by 2 epsilon naught nh. Let this be equation 5. Substituting equation 5 in 3 and simplifying, we get Rn is equal to epsilon naught n square h square by pi me square. Let this be equation 6. By substituting n equal to 1 in the above equation, we get the radius of the innermost orbit, which is Bohr's orbit and is represented by A0. Given A0 is equal to epsilon naught h square by pi me square. Substituting the value of Planck's constant h, epsilon naught, and the magnitude of the charge of the electron E, and simplifying, we get A naught is equal to 0.529 into 10 to the power minus 10 meter, which is equal to 0.529 angstrom. From equation 6, it is clear that the radii of orbits are directly proportional to n square. According to Rutherford's model of the atom, the energy En of an electron for a particular orbit of radius Rn is equal to minus E square by 8 pi epsilon naught Rn, where n is the principal quantum number. Let this be equation 7. Substituting the value of Rn and simplifying, we get En is equal to minus me to the power 4 by 8n square, 8 square, epsilon naught square. Let this be equation 8. Substituting the values of m, e, epsilon naught, h, and simplifying, we get En is equal to minus 13.6 by n square electron volt. Let this be equation 9. The negative sign of the total energy of an electron moving in an orbit means that the electron is bound with the nucleus. Substituting n equal to 1 in equation 9, we get the energy of the first orbit, E1, is equal to minus 13.6 electron volts. This is the lowest energy state of the atom and is called the ground state. Thus, the minimum energy required to remove the electron from the ground state is 13.6 electron volts. This is called the ionization energy of hydrogen atom. When an electron gains enough energy to go to higher orbits, the atom is said to be in an excited state. By substituting n is equal to 2 in equation 9, we get the energy of the second orbit, E2, as minus 3.4 electron volts. Similarly, by substituting n is equal to 3 in the expression for En, we get the energy of the third orbit, E3, as minus 1.51 electron volts. So, to excite an hydrogen atom from ground state, where n is equal to 1, to the first excited state, where n is equal to 2, the energy required is E2 minus E1. This is equal to minus 3.4 minus 13.6, which is equal to 10.2 electron volts. Similarly, to excite an hydrogen atom from the ground state, where n is equal to 1, to its second excited state, where n is equal to 3, the energy required is E3 minus E1. This is equal to minus 1.51 minus 13.6, which is equal to 12.09 electron volts. When the electron falls from the excited state to its ground state, it emits a photon whose energy is equal to the energy difference between the excited state and the ground state. For example, If the electron comes to its ground state from the first excited state, the energy difference will be E2 minus E1 equal to 10.2 electron volts. And thus, a photon of energy 10.2 electron volts will be emitted. We can observe the various energy states of hydrogen atom in the form of an energy level diagram as shown. In this diagram, the 0 electron volts corresponds to an energy of n equal to infinity, which is the highest energy state. This is the energy when the electron is completely removed from the atom and is at rest.
दोस्तों, यदि आज की वीडियो आपको अच्छी लगी हो तो लाइक कीजिए, चैनल को सब्सक्राइब कीजिए और अपने दोस्तों के पास इस वीडियो को शेयर कीजिए। अगर आपका कोई कमेंट हो तो कमेंट बॉक्स में नीचे जरूर लिखिए। थैंक यू।